Okay, today is Translations Day B, and overall we're just talking about translating, or translating is actually sliding graphs, but these are transforming graphs in many different ways. So let's just clarify that. Transformation as opposed to translation. Translation means you take something like a parabola and you slide it left, right, down, up. That's a translation. That's the easiest kind, moving them left or right or up or down. Okay, transforming them could imply a lot of different transformations. You could flip them over. Do you remember what makes them flip? What little thing? A negative in the right spot will make it flip. And you can also stretch them. You can also shrink them. You can also, lots of things. Technically, there's dilations. We never get into that. But anyway, this is all about transformations. And what we've done so far, you should know by now that things that are in here are the horizontal things. Horizontal on the inside, and what's on the outside? Vertical. Okay, so this is horizontal changes. These are vertical changes. And anything in the front is also outside. So if there was like a 3 out there, that would be a vertical thing. All right, so I'd like to keep moving along here. So some people like a list. Here is a nice list for you. If it's adding inside, then you go left. If it's subtracting inside, then you go right. If it's adding outside, then you go up. And if it's subtracting outside, then you go down. Now, some people like the lists, but I'd rather just look at a big problem and talk about what all the changes would be. Okay, this is a parabola. How can you tell it starts as a parabola? Yes? Because it has a squared. Okay, so I have an x squared in it. I know it's a parabola. Now, there's a lot of changes to my parabola. Lots of changes. The first change, I'm going to start on the inside because generally speaking, have you heard that you're supposed to start with parentheses? Okay, so you can technically do it in different orders, but in my opinion, the best way to start is on the inside. So that right there is telling me to go, is that left or right 2? Left 2. And this is what kind of a flip, a reflection? Horizontal or vertical is what I'm getting at. Okay, horizontal's on the inside. This is on the inside. This is considered the inside walls right there. So this is horizontal on inside. So that is a horizontal flip. I want you to think for a second. If you have a parabola and you flip it left, right, do you see that it ends up just landing right on top of itself? And it really makes sense if you think about it, because if you have y equals something being squared, and then I make it negative, do you get it doesn't matter? Because it's going to get squared. See what I mean? If I didn't have the negative, or if I do have the negative, it's going to come out the same. See, it's a parabola. When you flip it left, right, you can't tell the difference. It lands right on top of itself. Okay, how about that plus 7 on the outside? What is that going to do to my parabola? Up 7, good. How about, wait a minute, there's 2 things here, just to separate them off. That 4, is it vertical or horizontal, first of all? It's a vertical change. Is that going to be a stretch or a flip? It's a stretch. And a 4 times something seems like 4 times bigger. Can you trust stuff on the outside? Yeah. So it is 4 times bigger. Okay. And how about this negative right here? Down. That is down or up. And is it, wait a minute, is it a flip or is it just moving it down? The flip in the down or direction. Okay. So this is an up-down flip. And really what you should ask yourself each time is vertical or horizontal. And how about that minus sign? Is it vertical or horizontal? This minus sign right here, is it telling me vertical or horizontal? Vertical because it's on the outside. Vertical, and then it's a flip, but technically you say reflection. Vertical reflection. And if you reflect something vertically, that's going to take a parabola, which may have looked like this, and flip it upside down and make it look like that. Yes? Just to clarify, a negative is what makes it flip. It's not the number, it's the negativeness. If it's negative, it flips it. And this stretches it, and if you wanted it to shrink, you would make it a decimal. Like if I take a number like 12 and I multiply it by something bigger than 1, it's going to grow. If I take a 12 and I multiply it by a decimal, it's going to shrink. So if I made this a 0.4 right here, then it would be a shrink factor. It would shrink it down to 40% as big as it was. Yes?
So are the numbers in front always the ones you take, like stretch, shrink?
Just to clarify, I could put this plus 7 in the front if I wanted to and say 7 plus. So you got to be careful about the numbers on the front, because there's numbers being multiplied in the front and there's numbers being added or subtracted in the front too. I like them when they're at the end because it makes it easier to understand, but you just said the numbers in the front. Well, it depends. So let me show you one. Y equals 7 plus x. Did that make it 7 times bigger? No, because I could just move the x to the end and go say, okay, it just moved it up 7. Okay, so it depends what you mean. But usually, when you're talking about a number like this, let's say I put an 8 here, the numbers in front usually are the things you're multiplying by. So yeah, those are the numbers that are going to tell you vertically what to do. Because remember, stuff on the outside is vertical on the outside. So that's a vertical stretch factor of an 8. That's 8 times taller than it used to be. Yes? Good question, but we never do that. But what I will say is, what if I put a 1/8? That's kind of like saying divided by 8, right? That would be a shrink. It would be 1/8 as big. So it might have been a tall shape like this, and it's going to shrink down and only be really short. Like that. Okay, so that's a big overview, and I think those help. So now let's talk about, here is like really basic. That is your basic parabola. Would you get to this blue slide and sketch me the basic absolute value graph? I hope you don't need to make an XY chart by now. I hope you kind of know how it looks. You got to recognize these. We're spending about 2 weeks in this chapter. Compare with the kid across from you. It's easy to get this one confused with a different one. You do have 4 of them that you need to know. Okay, so how do you tell? How do you tell? Like, I had some people saying, I think it's this one, but I can't remember. And somebody else saying, I think it's this one, but I'm not sure. Well, how can you tell for sure? You can always make a what? XY chart. And if you need to, you just stick some numbers in and see what happens. I stick in a 1, I get absolute value of 1 is 1. I stick in a 2, absolute value is 2. I stick in a 3, and I'm going to get a 3. And if I try negatives, it's going to be -1 goes in there and comes out +1. And then I can just basically graph those dots. So don't think of this as a memorized thing, in that I'd like it if you memorize it, but you can figure it out. It's sort of like 4 times 3. 4 times 3 is 12, and I'd hope you'd just be able to snap to that. But if you had to, you could make 4 and then do 4 3 times, and then you could just count up all the dots. Get what I'm saying? 4 times 3 is a thing you can do. You don't just have to memorize it. But boy, it's a lot faster if you can just say 4 times 3 is 12. It's also a lot faster if you can just go, that's an absolute value. Okay, what's another one that you have to know? Square root of x. That's the one on the left here. Square root of x, remember what that looks like? I like to call it a ramp. It's kind of a ramp shape. And again, if you were like, no, I didn't know that, well, you can always make an XY. And this time, though, you might want to pick like some strategic x's. Because if you happen to throw in like a 2, you'll be going, square root of 2? I don't know the square root of 2. So don't do 2. What works nice? 4. 4 and the square root is 2. 9 square root is 3. How about 0? 0 still works nice. Square root of 0 is 0. And how about even 1? 1. So 0, 0, 1, 1, 9, 3, and 4, 2. 1, 2, 3, 4, 2. There we go. There's your ramp shape. Okay, that is another parent you have to recognize. And this is called weird shape. It can be anything, but if I take that shape and I want to do something to it, like move it to the right, then I would say f of x, except I want to move it to the right 2 spots. Take a guess what I'd put in there with the x. A -2. That would move it right 2. So when I say take this function and make it f of x minus 2, I'm just basically using code to say move it to the right 2. And so I'm going to draw over it here. And so then I would take this and grab it and move it to the right 2. Wait a sec. Got to grab the black one. Ah, there we go. Right 2. There we go. The black one is f of x minus 2. And let's say I want to move it down 1. Minus 1. And then I actually grab the graph. Down 1. See what I mean? That one's moved right 2 and down 1. So if you don't know what the function is, like I recognize this one. That's the square root of x. What if you don't know what it is because it's a weird squiggly shape? Then you just call it f of x. All right. So this one, just tell me, where is this guy going to move? Right 2 and then up 4. Good. Now, there's the fast way and the slow way. In my opinion, the fast way is to make an XY chart and stick numbers into your XY chart. And I think you also make less mistakes that way. Because what happens usually is if a kid makes a mistake, can you see how easy this would be to do? Here is a kid who likes to just graph the points and move them. And they go like this, and then they go, okay, so that's -2, so that's left 2. And you see what I mean? They're not even thinking anymore, and what am I doing wrong? It's not supposed to be left 2, is it? It's supposed to be right 2. And all of a sudden, they're going to get it wrong. But kid who actually makes the chart and sticks in, let's say, a 1. Stick a 1 in here. I have 1 minus 2. What's 1 minus 2? -1 squared is 1. 1 plus 4 is 1 comma 5. And I go over 1 and up 5. Could I have messed that up too? Yes. But when I'm done, I know this thing should look like a parabola. And if I've done it wrong, it's probably going to be like, okay, here's my parabola, and there's one point way over here. And I'll be like, what? Oh, I probably did this point wrong. And I can fix it and put it in the right spot, and then I end up with my parabola. Because you know what it should look like. Okay, I think you hear me that I'm giving you the choice. If you'd rather graph the parent points and then move them, that's cool. If you would rather just make an XY chart right off the bat, then that would be good too. The kids who will get the straight A's on this will be able to do both. Because if you graph it the way I just showed you, and you end up with a graph like this by making your little chart, then you have to be able to be smart enough to check it and go, does that make sense? Tell me, if I did it and I got that graph, if you check it over for yourself, can you realize it's wrong? Yeah, what's wrong with it? It should be to the right 2, and I went to the left 2. And what else? It's supposed to be up 4, and I only went up 2. Okay. So, but if you only graph parent points and move them, you might not catch it because you'll think you did it right. Here's the parent. And you go, okay, now I'm going to go 2 to the left. And again, I'm doing it wrong. And I don't even know it. Because I'm thinking it's to the left, and it's supposed to be to the right. Okay? So this is the dangerous way, in my opinion, for making mistakes. 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And the other thing a kid will do is by accident only move this up 3 and not notice it. See what I mean? Now it's wrong. I think it's safer to make an XY chart. My dream kid does both. You make the XY chart, you graph it, and then you go back and look and say, did it really move 2 to the right? Did it really move up 4? That's the ultimate combo. All right. I want you to do that with this one. I want you to just make a quick graph of the parent one, and then you'll have to choose. Do I want to take and move my parent points, or do I want to use an XY chart, or do I want to do some of both? To me, some of both is the ideal. So make the parent one, and then make the moved one. It's called a translation of 7. And then compare it with the kid that I paired you with who's across from you in your row. Okay, so here's the recording again. We are checking out if you did this right. 114293. Those are the biggies. And of course, we should connect them, and it generally goes that way. Let's talk about its domain and range for a moment. I know I didn't ask you for this, but domain, do you remember which one of these is left, right? Which one of these is down, up? Domain is left, right. How far left will this function go? 0. It doesn't go forever this way. Because why doesn't it go forever this way? Because you can't stick negative numbers in there. See? So it goes to 0, and can it be 0? 0 works to, what's its furthest right? Infinity. 0 to infinity. And the range of this thing, how low does it go? 0 to how high does it go? Infinity. Can it be 0 when on its way down? Yes, it can. There we go. Okay. Now this thing has been moved. You could have taken this and like basically made a copy of it like this, and then grabbed it, put it over here, and then moved it where? Up 7. 1, 2, 3, 4, 5, 6, 7. Now if your tests allowed iPads, that would have been probably a pretty good way to do it, because you can just make a copy so quick and move it so easy. But I said the ultimate student would have some points that they checked with it. Like for instance, if you plug in 0 for x, you should have gotten, put in a 0, what do you get? 0, 7 is on my graph. And just try like one more point. If you get a couple points to match up, you know you probably did it right. So stick in like 1. If I stick in 1, what do I get out when I stick in a 1 here? 8. 1 comma 8 should be on my graph, and it is, and so I can tell I'm doing it right. So a little bit of XY chart checking will help a lot. I'm telling you, a lot of you guys, if you look at your last test, you only made little mistakes. You didn't like massively not understand. I could see this test going the same way. People just like, oh, I just moved it 5 instead of 6 or whatever. So double check yourself so you don't have to lose that point. Okay, moving on. This one, I don't recognize that parent function, do you? So don't worry about it. You just move it like you would move the square root function or the absolute value or the whatever. You move it according to these directions. So where is it telling you to move it? Right 2 and down 4. Now just to clarify, if I were you, I would move the points. Because again, you are taking this test on paper. You can't just copy it, grab it with your scissors, and drag it. Okay? So don't use the scissor drag tool trick here. Would you please take the dots and move each dot where you're supposed to move it according to these directions, and then connect the dots again. Do it right now. Check it. And I guarantee you, if we look close, when you check your partners, there's going to be at least 4 or 5 kids who will make a little mistake on this. It's so common. They'll move one of their points off a little bit, and they won't even notice. I'll notice, and you'll lose the point. So just be really careful. Math is a careful sport. If you, I'll give you an example of that. Did you know that the last time we sent something to a planet, Jupiter, the mission was a complete failure because when they went to go into orbit around Jupiter, the thing crashed into Jupiter. It didn't set up its orbit correctly. They tracked down the mistake, and it was a conversion between feet and like meters. All it took was that, and it crashed billions of dollars worth of equipment. And can you imagine all the time it took to get it up in the air and to get it there, and it finally gets there, and you're just about to get data out of it, and because somebody made a stupid mistake, it cost billions of dollars, and all those people were just wasting their time. So my point is, that there are times when things, it matters to be, you know, off a little bit. You know, one little oops on something and you can make a huge difference. Especially when you're doing something like millions of times. McDonald's, for example, sells so many cups of coffee that if they do something wrong that costs them just a couple pennies on each cup of coffee, it can actually cost them millions of dollars a day in coffee sales if they make a 2-cent mistake. 2-cent mistake on their pricing on their coffee. Like for instance, let's say that they spent 2 extra cents on the cups that they didn't have to spend because they didn't get a good enough bid or whatever on the cups. 2 cents for each cup will make millions of dollars a day. One of the reasons that they spent so much money. Did you guys hear about the coffee lawsuit with McDonald's? The old lady gets burned by the coffee, and everybody's like, "Come on, old lady, you shouldn't be putting your coffee in your lap," and then blaming McDonald's when the cup doesn't work. But here was the rest of the story on this. I don't know if you'd heard this. McDonald's had been warned several times in previous lawsuit kind of situations that they weren't supposed to brew their coffee that hot. And so when this lady got burned, it was kind of like, we warned you over and over again, you can't make that mistake of having it that hot. Turns out they were doing it because they could save a lot of money on coffee grounds. And so when they gave her the $2 million for her coffee burn, it actually represented 1 day's profit on coffee. They gave her just the profit that they had made that day on coffee sales. And so when you have things that are a huge multiplier, you make a little 1-cent mistake, it can multiply by like 1,000,000, and all of a sudden you got some serious money. Okay, all I'm trying to say is, I know some of you think, if all I did was a dumb mistake, how come that really matters? Math is something that rewards careful people, so you gotta be careful. Okay, right 2, down 4. Right 2, down 4. First dot is there. Everybody check yours and see if you have a dot right there. Good. Next one should be right 2 and down 1, 2, 3, 4. Puts it right there. And that would be at 1, 2, 3, 4, 5, comma 1. The next one, right 2 and down 1, 2, 3, 4, is there at -2, or 2, -2. The next one, right 2 and down 1, 2, 3, 4, should be right there on the y-axis at 3. And the last one, right 2 and down 4, 1, 2, 3, 4, is right there. And then I just connect my dots. Any questions on that? Okay, that's the main new thing for today is weird shape. Okay, let's not even do this one. Just tell me, you would take each corner and you would move it where? Left 2 and then down 3. That's all there is to it. All right, good enough. So on this one, if we did move the parent, which is a what shape? Parabola. We'd move it which way? Left 5 and then down 1. And when I move a parabola, which generally looks like this, left 5, 1, 2, 3, 4, 5, and down 1. That was not a graph, that was a sketch. So on your test, you'll be expected to have 5 good quality points. The vertex, and then a couple on each side of the vertex. Like there'd be one here, and 1, 2, 3, 1, 2, 3, 4 there, and 1, 2, 1, 2, 3, 4. See how I actually goofed that up? So now that I got my points in there, I can see that I wasn't super accurate on my little red swoosh line there. This is not a sketching test. This will be a graphing test. Now the domain and range. Domain, left, right. Range, down, up. It's really easy to, by accident, put up, down, because that's what you want to say naturally. Down, up, because the lower numbers, the smaller numbers always got to be first. Would you please figure out the domain and range of this function and compare it with the kid sitting next to you? Try domain and range for this. Compare with them. Okay, so the domain and range were negative infinity, positive infinity, and the range was -1 to infinity. Okay, I was just explaining why you needed the bracket, because You need the bracket because -1 actually works in the function. All right. This is just so simple. Don't stress on these. You just have to write an equation that matches what they want, which is how do I move this up 4? I take the x, and how do I go up 4? Do I put it inside or outside? Outside, and I say plus 4. Easy peasy. Okay, now there's one other kind that's like this, though, that's not super easy. And that's where you have a graph that's already made. Let me make one like this. And they say, I want to do this. And I know you know that this is 4 to the left and down 6. That's not the issue anymore. By now you should have that. But what if I want to take this graph, which has already been moved, and move it again to more to the right than it used to be, and down 1? Got an idea? So you want to put a 2 here and a 1 here?
No.
No? But kind of.
Yeah.
Tell me.
Well, if you're taking the -6,
Yep.
and then you're moving it down another 1, could you just make it a -7?
Yes. So I'm going to think of it this way. Moving down 1 takes away another 1. And going 2 to the right, is that going to be a +2 or a -2? 2 to the right, is that minus or plus? Right is minus. We're on the inside, remember? It's opposite of what you'd think. Right seems like it's plus, but it's minus. You get what I just did there? Now, the answer would be y equals, this x plus 4 would turn into, when you subtract 2, x plus 2, and this becomes a -7. Okay, that's the hardest kind, but I think that isn't that bad. Okay, one more like that to see if you really got it. Let's say we had y equals negative absolute value of x plus 2 minus 8. And then I wanted to go up 9 and left 4. Would you figure out what the new equation should be? Got a question? Awesome. Answer it on your paper. Don't let the negative in front freak you out. It just means that the whole thing is reflected or flipped upside down. You still have to move it up 9 and left 4. Okay, up 9. How many of you put a plus 9 on the end of it? Good, that's what you should have done. And how about left 4? Plus 4. And we put it all together, and you'd have y equals negative absolute value of x plus 6, and that makes plus 1. All right, so that one is final answer. Up 9 plus 9, left 4 plus 4, y equals negative absolute value x plus 10 plus 10. Raise your hand if you had that one right. Oh, did I do something wrong? A lot of people are. Oh, I'm doing it again? Okay. Sorry. I kind of lost my train of thought when they interrupted with the announcement. So apparently I had already moved it up 9 and left 4. I just moved it up 9 again and left 4 again. So, all right. So what do we need to do on, there's a few other kinds of problems, but they're the same thing we've been talking about. This is like directions. What does it say to you? Take the function and move it. Always start on the inside. Move it where? Left 4. And what's this plus 3? Up 3. Even though it's in the front, it's still just a plus 3, just as if it was back here. It's the same thing. All right? So that one's left 4 and up 3. All right. And this one, I take this and I move it. That's just directions on where to move it. Left 1. You take the parabola and move them left 1. All right, so how would I write that then? If I had f of x is x squared, I want to move it left 1. Well, now you just have to go like this. Left 1. There. This one is moved to the left 1 compared to that one. And this one, f of x, is absolute value of x. And what do we say we wanted to do to it? Move it 4 to the left. So I just go like this, left 4. And then I'm going to move it up 3, up 3. So think of this as just a fancy way of telling you, hey, buddy, move it left 4 and up 3. That's really all it's doing. Okay, so you've learned a lot of stuff. And tonight's homework is the worksheet, of course, called Translation B. I want to look at it with you for a second, see if we can cut it down in size a smidge.